Hello everyone. I wanted to change topic a little bit in the course right now. So till now we've talked about scalability of computation and blockchains, and we talked about two papers, or actually three papers: TrueBit, Yoda, and even Tuxedo, right? And they allowed us to increase the computation in a single transaction. Right? So now I want to change focus and look at pure proof of stake protocols. So all the papers that we've discussed till now in the course would apply to proof of work, right? And we didn't really particularly talk about the consensus protocol. And in the earlier course, we had looked at proof of work plus proof of stake protocols. We looked at things like Slasher, for example, by Buterin. And of course, we had another sort of naive proof of work plus proof of stake protocol where every nth block had proof of work, but the rest of the blocks had proof of stake. Right? So nowadays, but of course, people don't like proof of work for the reason that it consumes a lot of power. Right, and so people prefer proof of stake, but we saw that proof of stake has a lot of issues like nothing at stake problem and so on, right? And I mean, you could have all the problems that you have with proof of work, like forks and so on, but at the same time, there were additional problems like long range attack, nothing at stake, and bribe attack and so on. Okay? So people have been thinking about proof of stake. Can we have consensus with only proof of stake and avoid many of those problems? And Algorand is one of the first proposals which claims to achieve, things like safety and liveness, but with using only proof of stake without using any proof of work. So Algorand was proposed by a team of researchers, and one of them is somebody called Silvio Micali, and he's a Turing Award winner. So that's equivalent to the Nobel Prize in computer science. Okay, so let's start maybe by having a recap of the different protocols we studied in the last semester. So first of all, we had permissionless blockchains. And then we had permissioned blockchains. And what were examples we looked at here? We looked at things like Raft and PBFT. So these were the protocols, and we had permissionless protocols like proof of work, then standard, let's say vanilla proof of stake, right, and so on, right? So there were some trade-offs between these. So the good thing about permissionless was the number of miners could be, I mean, in theory, could be any number, infinite in theory, no restrictions. And these protocols, we needed to know how many were there. So n was known, the total number of miners, right? So of course, we shouldn't call them miners in the permission setting, but let's just call them consensus nodes. What about forks? Could we have forks? And here actually in a permissions protocol, we actually don't have any forks, right? So this idea of a fork is something new which comes in the permissionless setting with proof of work. So here, I mean, the nodes decide on a particular block in the blockchain, and that's the end of it. I mean, you don't have to worry about a block being removed at all, right? So here, of course, we have to deal with forks. Forks do occur. So what about the throughput? Okay, and well, of course, it depends on how we define throughput, whether it's in bits per second or whether it is in terms of transactions per second and so on. But let's talk about it in bits per second. So here, assuming that we have Bitcoin, we have 1 MB block coming every, let's say, every 10 minutes, right? So that roughly gives you kilobits per second, whereas in a permissioned setting, you could have something close to the line rate. So this means that sort of you take the link rate of any particular node. If it's like 1 gigabit per second, in theory you can get something close to that, maybe with a slight constant factor of, right? What about assumptions of honesty? So here pretty much we have 50% of hashing power, right? And let's say stake, right? If you're looking at a vanilla proof of stake, you definitely need at least 50%. Right? If it's less than 50%, then nothing is going to work. You can do a 51% attack, right? And here, here we expect at least 2/3 to be honest. Okay, so 2/3 of n net should be honest. Okay, so of course with more stricter assumptions on delay and so on, you can reduce this to something like 50%, right? But in general, for safety, you need 2/3 at least to be honest. Okay. What about the transaction confirmation time? So for Bitcoin, it is 10 minutes. And well, here, what is it going to be? Well, in something like PBFT, you need different nodes to communicate with each other. So it really depends on the round trip time. So it depends on the network delay. So if the network delay is of the order of, let's say, tens of milliseconds, then in theory you can have confirmation of a transaction in tens of milliseconds, but let's just say hundreds of milliseconds. Okay, so you have a few rounds in PBFT and then you have consensus. So because in Bitcoin you can have forks, typically I mean, you have to, it takes some time for a transaction to get into a block, and then of course you have to wait for several blocks for confirmation, right? So 10 minutes is of course the minimum, but okay, so if everybody was honest, maybe you could have roughly 10 minutes for a transaction to get in, but let's say that it could take, let's say, several blocks, so let's say up to 60 minutes, right? Then but there are certain advantages also to permissionless. So can there be a DDoS attack? Okay, so what is a DDoS attack? Well, it's a distributed denial of service attack, where let's say you flood the network link of one particular node so that it cannot receive any messages, right? And so of course this is a distributed system in both cases, so it's harder to do a DDoS attack. But since there are n nodes here, if you know the IP addresses of these n nodes, it would be easier to do. So I would just say it is less resilient. But here it is more resilient because the number of nodes are higher, right? And of course you may not know the IP addresses of all the nodes. That may be possible also, right? And there could be thousands or even tens of thousands of nodes, so to do a distributed denial of service attack on all of them would be difficult, right? What about safety? So we said in the last course that safety means that nothing bad happens. Which means, and in our particular case, it means a block getting removed. So can a block get removed here? And of course, because of forks and private chain attacks and so on, that could happen. So there is only a probabilistic guarantee. So you can say things like, with high probability, once a block is in a chain for, let's say, 1 hour, it's unlikely to be removed, right? But there is no hard guarantee. Whereas here you do have guarantees. So let's say less than 1/3 is Byzantine. What about liveness? So liveness means that transactions of, let's say, honest users keep getting into the chain. Okay, over time. So the chain is sort of alive, that you offer a transaction to it and it gets in, right? So liveness, of course, even in Bitcoin is guaranteed. So we are really talking about Bitcoin. Here, and of course it would follow for Ethereum and so on. So here we do have a guarantee. Okay, so there is some miner who's going to, honest miner who's going to once in a while generate a block, and he takes these honest transactions, puts them in and sends them off, right? So it's possible that those blocks get removed later on, with some private chain attack and so on, but at least one would expect that the honest blocks get into some longest chain once in a while, right? And there are formal proofs for this. So later in the course, we will look at some of these papers which actually formally talk about safety and liveness in a very general setting for proof of work chains. Okay. So even if a network partitions, in fact, we can have liveness because each of the users might see a different blockchain. There's a partition because of communication gap between the, let's say, different sets of miners. But these honest transactions will get into blocks into at least one of those chains. Whichever set of miners hears these transactions, they will put them in their blocks. So even when you have partitions, you do have liveness. Okay. But here, of course, we don't have those sorts of things. I mean, you have actually some sort of impossibility theorems, which talk about things like things like the cap theorem, where you may not have liveness with partitions, right? I mean, depending on the situation and so on. But anyway, what we know for PBFT that given some synchronous assumptions, you can have liveness. Okay, so given a certain delay or a bounded delay on the transactions or the exchange of messages between nodes, you do have liveness. Okay. So this is sort of the difference between permissionless and permissioned. And really, permission blockchains have lots of scalability issues. We've looked at one of them, scalability of computation, but scalability of transactions to transaction throughput is a big issue. You can't put in too many transactions in Bitcoin, right? And you might want to think, what about Tuxedo and Yoda and so on? Can you scale up the transaction throughput arbitrarily there? And when you have proof of work, and it turns out that's not quite the case. Right, so we are able to have individual transactions which have a lot of computation, but the number of transactions may not be very high. Right? And anyway, of course, Algorand came out in 2017-2018 time frame, right? And so the state of the art at that time were things like this, like proof of work with vanilla POS, PBFT and so on, right? And there were a few other protocols, of course, being proposed. So what are the shortcomings here? Of course, one of the shortcomings is that there are only n nodes. You can't have an arbitrary number of nodes, so it is not permissionless, right? And if somebody can bring down these n nodes or control them like a government, then you're in trouble, right? And one of the strengths of Bitcoin is it's very hard for anybody to bring it down. So what has happened is that even when big countries like China or so on ban mining, what happens is the miners just ship their hardware to other countries and then the mining starts in those other countries, right? And never does, even you might have a temporary dip in the hashing rate, but that's about it. So Bitcoin is very, very resilient, right? But the problem is that it consumes a lot of energy, right? And plain proof of stake protocols have other issues like nothing at stake and long range attack and so on. So what the authors of Algorand wanted to do is they wanted to have the best of both worlds, of the permissioned world where you have higher throughput of transactions, right? But at the same time, you have any number of nodes which can participate in the protocol, so it is permissionless. Okay. So what Algorand claims to do is, under certain circumstances, there are no forks. So maybe we should say with high probability. Okay, so I mean, it's almost like PBFT type of protocols. I mean, you don't have to worry about forks at all. Once a block is decided on, it's going to be there forever, right? And also you have higher throughput in terms of transactions per second than Bitcoin. Okay, and at the same time it is permissionless. Okay, and of course no energy consumption. I should say consumption due to POW. Rather than just saying no, just let's say low energy consumption. Okay, but it's negligible. Of course, each node will have to do some computation to maintain the blockchain and so on, but there is no such thing as hashing, right? So Slasher, which we looked at in the last semester, had a little bit of POW, right? And vanilla POS had things like forks and in fact heavy problems due to forks. Somebody could go back all the way to the Genesis block and start a fork, right? And do something like a long range attack. So this seems too good to be true, right? But under certain circumstances, and we could argue whether those assumptions are realistic or not, but under those assumptions, Algorand proves mathematically that it gives us these different properties, right? So Algorand made some big waves, especially since the team was very strong, right? Like by Silvio Micali and so on, and the paper appeared at some very well-reputed conferences in computer science. Okay, so let's just list these down. No forks, higher throughput, permissionless, this, and what about liveness? So under some synchronous assumptions, okay, so any number of minors. Okay, so higher throughput due to faster consensus. So roughly 1 minute for a 1 MB block. So how are we going to achieve this? Okay, so that's something to think about, and really what Micali and others were thinking was in terms of something like PBFT. Right? So can you do something like PBFT but in a permissionless setting? And that's sort of what they were thinking of. So how can we reduce a permissionless setting to something like PBFT? Okay. And one thing that you might think of doing is that can we elect certain of these based on the stake of users? Can we elect them to form committees? And once you form a committee, can you do something like PBFT? Okay, so that's one idea. So let's note that down. So use stake. So what is stake? Well, it's the let's say number of coins owned by users, right? So can we use this to elect a committee of, let's say, n users, and getting exactly n is going to be hard, so but roughly n users, and then use some sort of BFT protocol, some Byzantine fault tolerant protocol. Okay, so can we elect a committee, and for BFT to work we want at least 2/3 to be honest. Okay. And suppose we are able to do that, then why not just let them run BFT, right? So of course then the question is, in something like PBFT we needed some sort of a leader, right? So the leader is going to propose a block, and others are sort of going to vote on it. Okay, so let's write that out. So finally, of course, we're going to look at the protocol in detail. So this is just an idea. So the question is how to elect a committee. So everybody has to agree on the rules, and everybody has to agree about who is going to be there in the committee or not. Okay. Okay. And we've seen in an earlier class in Yoda how to elect this execution set, which is what we called it, right? And of course we had borrowed ideas from Algorand. So we're going to use a similar idea. So based on the stake of users, so you're basically going any particular miner, or let's say user with some stake. Suppose he has a public key and a private secret key, right? So these are going to be used in some election protocol to say whether he is elected to the committee or not. And of course we are going to not just put this, so this I'm just putting this as a concatenation sign. We have to put the stake of the user. Okay, so the amount of stake he has on the blockchain. So everybody knows the public key and the stake. So instead of saying like in vanilla proof of stake whether I am going to create the block or not, right? And we had a timestamp also we were pushing in. Here I am just going to say whether I am elected or not to the committee. So there has to be some other information, some sort of a seed. Okay. So let's also put some common seed which everybody has, and this has to be a little bit random. Okay, so at least every time we choose a committee we want the seed to change in some way, right? So based on all of this information, there has to be some method, some election protocol which says whether I am elected or not, right? And once we are elected, we can do something, some sort of a BFT protocol to decide on what the next block is going to be. Okay. So how do we elect a committee? So this is roughly what we are going to do. And next question is how to choose a leader. Okay, so we are going to fall back on something like PBFT, where there is a leader who's going to propose a block. Okay, so we'll have to come up with a method to do this, right? And then the question is how to make this DOS resilient. Let's say DDoS or DOS resilient. Okay, so DDoS is just a special case of denial of service attack where the nodes launching the attack are distributed, right? So any sort of denial of service attack, how are we going to make the committee resilient to it? So one of the advantages of something like Bitcoin is it's DDoS resilient, but we said if there are n nodes, like in a PBFT protocol, then all n nodes, let's say n is equal to 10, then you have to bring down 10 nodes, right? And now, because we are looking at something like PBFT, we are going to run into problems because if everybody knows who's in the committee, then again we are likely to be brought down by a DDoS attack. So we want to be DDoS resilient, and what we are going to do here is it's sort of like a shoot and scoot solution. So of course the authors don't use this term, but I'm using it. So what is shoot and scoot? It's usually used in a negative sense where somebody shows up, fires a bullet and then runs away, right? So normally that's a negative thing. But here we are going to do something like that, but in a positive sense. So what we are going to do is we are going to come up with a committee. So the committee speaks, and the committee is no longer valid after that. It sort of disappears. So committee members talk, so they announce something and they broadcast that. So it's very hard to stop a broadcast. Right, we are assuming a connected network between honest, let's say, nodes who are running the network. Right, so once a node is elected, so first of all, we are going to do a secret election. So first of all, only a node knows if it is elected. And the reason is because the secret key is used. Nobody else knows the secret key, so it has other nodes have no idea if a particular node is elected or not. Right? So, but in addition to that, what they do is they talk once, they announce something, and then play no further role. So they play. Okay, so let's say that committee proposes a block, and it's not that they go to a second round like in PBFT, right? So in PBFT first there is a prepare, and then there's a pre-prepare and then a prepare and so on, right? So that doesn't happen over here. So I'll just write that recall in PBFT. So the same committee did this. Then there was a commit, right? So roughly there were these three, and then of course there was a reply and so on. Okay. So these are liable to DOS. So once you, let's say once a node announces that, here is my block, that node can be brought down, right? Or when a node, these are sort of gossip rounds. And here they talk about what did I hear in the pre-prepare stage, am I willing to accept this and so on, right? And then what did I hear in the pre-prepare round and so on, right? So this is what we looked at in detail in the last semester. Now we want to avoid this because it's a permission. We want it to behave like a permissionless setting. So I don't want people to know who are part of the committee, right? And so if somebody has said something in this round, he should not even belong to the next round. I just want him to propose something and then disappear after that, right? So this is why Algorand is going to look somewhat and in fact quite different from PBFT, right? So different nodes can propose things and then they disappear, but then in the next round you elect a new committee which is going to vote on everything, right? And it's not as simple as PBFT where you have just 2-3 rounds and then you're done, right? Even if let's say the node proposing the block, the leader is honest and it proposes a single block, you may have to go on for many rounds, right? Because here each node is saying what did I hear, and once you have a quorum, for example, you're done, right? Because what everybody sort of has heard. So you have to do something like a quorum over here, but you have different committees being formed, and somehow we have to converge to a particular solution, right? So it's going to look a little bit more tricky, and what we are going to try to avoid is we are going to try to avoid re-election of a new leader and so on. Okay, so what we want is, let's say, a new committee in every round. And in PBFT, if the leader misbehaved, we had a re-election, and we want to avoid that over here. Okay, so how are we going to do this? Okay, and first let's talk about how to elect nodes. So this is used for committees in different rounds, right? And it's called cryptographic sortition. So it's an idea which could be used for different protocols. Of course, it was proposed by the Algorand folks, but we use some ideas of sortition in Yoda. Okay. So what we're going to do is not just this which I've shown over here. Okay, so here I'm just saying am I elected or not. Okay, so this is a binary thing, but let's think about it. Suppose the stake was very high, shouldn't somebody have a higher chance of getting elected? Because if it's of course not just that, maybe you want to be elected multiple times. Okay, so that's what Algorand is going to use. So there will be a certain number of people let's say there's a target for n people in a committee, and you may get a little bit higher or a little bit lower than that, just the way this cryptographic sortition works. But somebody who has a lot of stake might be elected multiple times to that particular committee. Okay, so sortition is going to say not just am I elected or not, but how many times am I elected. So you could be elected 0 times, but you could be elected, let's say, 5 times to the same committee. So then you would have a voting corresponding to 5 votes in that committee. Okay, so cryptographic sortition is going to give us that. So how many times am I elected to a committee so this is one thing it's going to tell you, and only the user knows. This information. Okay. So this is important to prevent something like a DOS attack. Okay. So one of the things used is called a verifiable random function. Okay. So what is this VRF? So given some input string, so this could include things like the seed, which is common to all the users and so on. What we are going to do is we are going to get, so this is going to give a hash and some pi. So this is something like a typical hash. So this is uniquely determined by the secret key and this X. Okay. But is random to other users. Who does not know SK. Okay, so fair enough. So somehow we have to plug in into this function X and SK, and we get something which looks like a hash. Okay, and so let's say that the length is hash len bits, right? So this could be something like 256 bits or whatever. And now this is a proof, pi is a proof, so that's where the term verifiable comes in. So it's a proof that hash was created by the secret key So this was, of course, you don't want people to know what the secret key is. So all that they know is the public key. Okay, example of a VRF to understand. So suppose signature of X with SK is given by this. Okay. Now suppose I take a hash of this. This is the hash output of VRF. So I take a hash and I just take the hash of this signature. Right? Okay, so I mean, cryptographers may not be convinced that this is going to give something totally uniformly distributed, and with all the properties of a hash function, irreversibility and so on. So we are just going to send this through a hash function, right? And let's say that this is the hash. Okay. Now, what is going to be pi? Okay. So so does this have the properties that we wanted for hash? Well, it's uniquely determined by Sk and X. That's true. But it is random to anyone who does not know Sk, right? So so nobody else can sort of guess what this hash is going to be, right? Because they don't know what Sk is, right? Okay. And of course it is uniformly distributed, let's say, over the space, because hash function has that property, let's say. So what is pi? What is the proof? Well, the proof is actually this itself. Okay. So suppose, so this is known to all, X is known to all. So the public key and X is known to all, right? So does this have the property of pi? So suppose a user tells me that this is my signature, right, for X, then using the public key, anybody can verify that this is indeed the signature of X using Sk. Okay, so that's how public key cryptography works. You don't know the secret key, but you can verify that the signature indeed was signed by this secret key, and you can verify this using the public key. Okay. So we can check, and then we have this hash value, right? So this, of course, you can check is the correct hash value, because you just have to send this pi through a hash function and you get it. right? So initially, of course, suppose we are going to use this somehow to elect somebody to a committee. How we are doing it, we'll talk about in a moment. But suppose we are going to use it, let's say somebody elects himself, and then later on he wants to prove that he was part of the committee. What does he have to do? Well, he would just have to provide this proof, right? And he can also provide the hash value, right? Or in fact, in this particular simple case, where hash is just a hash value of pi, you just have to broadcast this and everybody knows that your hash value was so and so, right? Okay, so suppose we are able to do all of this. Now how are we going to elect somebody? We could use this as a VRF, but of course there are better VRFs which people can propose, where you may have better properties and so on. Okay. But suppose we use this, how are we going to elect somebody to a committee, right? So this hash is roughly, let's say, between 0 and 2 to the power of 256 minus 1. Okay. So how to randomly elect a user to a committee? Using his hash number which comes out, right? Which could be defined this way. Okay. And you might say that let's put a threshold. If you're less than a threshold, so this hash value, let's say, is between 0 and 2 to the power of 256 minus 1. Okay, assuming that hash length is 256 bits. So we could put a threshold. Okay, and let's say if this hash value is less than the threshold, you're in a committee or not. Okay. Now a problem, we run into a problem here, in that what somebody could do is that he could divide his stake into multiple accounts, and each of them is going to give him a particular chance of getting elected to the committee, and he would have a higher chance of getting elected, right, using this method. Okay, because really your stake has not been taken into account over here, only your secret key and X has been taken into account, right? So somehow we have to bring in the stake also, and using this naive method is not going to work. Okay, so this naive method, it's prone to a Sybil attack. So what we are going to do is the following. So there is something called the sortition function, which we give as input the secret key. We're going to give the seed which everyone knows. We are going to give some tau, so this is also known to all. So this is some sort of a threshold. And there's something called a role. So we'll ignore this for the time being, but I mean, roles could change, like somebody could be a leader, or somebody could, in the different rounds they have different roles and so on. We have W, which is the stake of the user. So stake corresponding to this public key secret key pair, and capital W, which is the total stake in the system. So this total stake is important because we want to elect a committee of a certain size W, of a certain size N. This is what we want. and we're going to, so this is going, so roughly your chances of getting n should be proportional to w, small w divided by capital W. And of course, if your small w is higher, then you might be elected multiple times to the committee. Okay. So what is the sortition function? So what we are going to do is we are going to first of all use the VRF, and we are going to feed the seed and the roll in. Okay, and we are going to get some hash and pi. So this of course would be used later on to prove to somebody else that this particular user is part of the committee or not, or how many times it was elected and so on. Now we have a variable p which is going to be set to tau divided by w. Okay. So of course W, let's say, is fixed in the blockchain, whatever, for the timing, right? Let's say there's 21 million Bitcoin or whatever, and depending on what size you want, number of users, you set this tau appropriately, right? So the larger tau is, the more chances of users getting elected. Okay, so this is like sort of a normalized value of tau. Okay, and so J is going to be the number of times that a user is elected, and I'm going to initialize it. So now comes something tricky, which we will have to understand it in the next class. So we have a while loop which is going to figure out how many times we are elected, right? And we're going to exit the while loop after the number of times we are elected, right? So what I am going to do is I am going to take the hash value, okay, because I want some random selection for this user, 2 to the power of hash length. Okay, so this is the normalized value of the hash. This is between 0 and 1. Now if this is greater than or equal to this binomial function, okay, so we're going to compare this value to some of these particular binomial terms. Okay, so I'll just write this here, where B K W P is equal to W choose K. So we are assuming W is a positive integer. P to the power of K 1 minus P to the power of W minus K. Okay, so this is how we define this. Okay, and we are going to essentially increment J every time we go through this loop, right? And okay, so what are we doing? We are choosing hash and pipe, of course, based on the VRF that is given by this secret key and this input. What we are doing is we are normalizing this tau threshold with the weight, really the total weight of stake in the entire blockchain, right? We initialize the number of times somebody is elected to 0. Okay, so by default you have 0, you've been elected 0 times, but if your hash value is high, for example, you could be elected multiple times, which is given by this while loop. Okay, so the intuition of this what we are doing here, we'll look at in the next class. But anyway, what does this return? So we are going to return what the VRF gave us and J, the number of times we are elected. Okay. So this J is called the number of sub-users of user with these particular keys and stake small w. So we look at the intuition of this particular sortition function or this particular while loop, and we look at other aspects of Algorand 2 in the next class.